that, within the framework of the applicability of its basic concepts, it will never be overthrown. Albert Einstein. After studying this unit, you will be able to times explain the terms, system and surroundings, times discriminate between closed, open and isolated systems, times explain internal energy, work and heat, times state first law of thermodynamics and express it mathematically, times calculate energy changes as work and heat contributions in chemical systems, times explain state functions, U, H times correlate U and H, times measure experimentally U and H, times define standard states for H, times calculate enthalpy changes for various types of reactions, times state and apply Hess's law of constant heat summation, times differentiate between extensive and intensive properties, times define spontaneous and non-spontaneous processes, times explain entropy as a thermodynamic state function and apply it for spontaneity, times explain Gibbs energy change, G, and times establish relationship between G and spontaneity, G and equilibrium constant. Chemical energy stored by molecules can be released as heat during chemical reactions when a fuel like methane, cooking gas or coal burns in air. The chemical energy may also be used to do mechanical work when a fuel burns in an engine or to provide electrical energy through a galvanic cell like dry cell. Thus, various forms of energy are interrelated and under certain conditions, these may be transformed from one form into another. The study of these energy transformations forms the subject matter of thermodynamics. The laws of thermodynamics deal with energy changes of macroscopic systems involving a large number of molecules rather than microscopic systems containing a few molecules. Thermodynamics is not concerned about how and at what rate these energy transformations are carried out, but is based on initial and final states of a system undergoing the change. Laws of thermodynamics apply only when a system is in equilibrium or moves from one equilibrium state to another equilibrium state. Macroscopic properties like pressure and temperature do not change with time for a system in equilibrium state. In this unit, we would like to answer some of the important questions through thermodynamics, like, how do we determine the energy changes involved in a chemical reaction process? Will it occur or not? What drives a chemical reaction process? To what extent do the chemical reactions proceed? Unit 6 2019-20. Thermodynamics 161 6.1 Thermodynamic terms. We are interested in chemical reactions and the energy changes accompanying them. For this we need to know certain thermodynamic terms. These are discussed below. 6th January 2001. The system and the surroundings. A system in thermodynamics refers to that part of universe in which observations are made and remaining universe constitutes the surroundings. The surroundings include everything other than the system. System and the surroundings together constitute the universe. The universe is equal to the system plus the surroundings. However, the entire universe other than the system is not affected by the changes taking place in the system. Therefore, for all practical purposes, the surroundings are that portion of the remaining universe which can interact with the system. Usually, The region of space in the neighborhood of the system constitutes its surroundings. For example, if we are studying the reaction between two substances A and B kept in a beaker, the beaker containing the reaction mixture is the system and the room where the beaker is kept is the surroundings. Fig 6.1. Be real or imaginary. The wall that separates the system from the surroundings is called boundary. This is designed to allow us to control and keep track of all movements of matter and energy in or out of the system. 6th January 2002. Types of the system. We further classify the systems according to the movements of matter and energy in or out of the system. 1. Open system. In an open system, there is exchange of energy and matter between system and surroundings. Fig 6.2. A. The presence of reactants in an open beaker is an example of an open system. Here the boundary is an imaginary surface enclosing the beaker and reactants. 2. Closed system. In a closed system, there is no exchange of matter, but exchange of energy is possible between system and the surroundings. Fig 6.2. B. The presence of reactants in a closed vessel made of conducting material, e.g., copper or steel, is an example of a closed system. Fig. 6.2. Open, closed and isolated systems. Fig. 6.1. System and the surroundings. Note that the system may be defined by physical boundaries, like beaker or test tube, or the system may simply be defined by a set of Cartesian coordinates specifying a particular volume in space. It is necessary to think of the system as separated from the surroundings by some sort of wall, which may *. We could have chosen only the reactants as system, then walls of the beakers will act as boundary. 2019-20. Chemistry 1623. Isolated system. In an isolated system, there is no exchange of energy or matter between the system and the surroundings. Fig 6.2. C. The presence of reactants in a thermos flask or any other closed insulated vessel is an example of an isolated system. 6th January 2003. The state of the system. The system must be described in order to make any useful calculations by specifying quantitatively each of the properties such as its pressure, P, volume, V, and temperature, T, as well as the composition of the system. We need to describe the system by specifying it before and after the change. You would recall from your physics course that the state of a system in mechanics is completely specified at a given instant of time, by the position and velocity of each mass point of the system. In thermodynamics, a different and much simpler concept of the state of a system is introduced. It does not need detailed knowledge of motion of each particle because we deal with average measurable properties of the system. We specify the state of the system by state functions or state variables. The state of a thermodynamic system is described by its measurable or macroscopic, bulk, properties. We can describe the state of a gas by quoting its pressure, P, volume, V, temperature, T, amount, N, etc. Variables like P, V, T are called state variables or state functions because their values depend only on the state of the system and not on how it is reached. In order to completely define the state of a system, it is not necessary to define all the properties of the system, as only a certain number of properties can be varied independently. This number depends on the nature of the system. Once these minimum number of macroscopic properties are fixed, others automatically have definite values. The state of the surroundings can never be completely specified. Fortunately, it is not necessary to do so. 6th January 2004. The internal energy as a state function. When we talk about our chemical system losing or gaining energy, we need to introduce a quantity which represents the total energy of the system. It may be chemical, electrical, mechanical or any other type of energy you may think of. The sum of all these is the energy of the system. In thermodynamics, we call it the internal energy, U of the system, which may change when times heat passes into or out of the system, times work is done on or by the system, times matter enters or leaves the system. These systems are classified accordingly as you have already studied in section 6th January 2002. Work. Let us first examine a change in internal energy by doing work. We take a system containing some quantity of water in a thermos flask or in an insulated beaker. This would not allow exchange of heat between the system and surroundings through its boundary, and we call this type of system as adiabatic. The manner in which the state of such a system may be changed will be called adiabatic process. Adiabatic process is a process in which there is no transfer of heat between the system and surroundings. Here, the wall separating the system and the surroundings is called the adiabatic wall. Fig 6.3. Let us bring the change in the internal energy of the system by doing some work on Fig 6.3. An adiabatic system which does not permit the transfer of heat through its boundary. Let us call the initial state of the system as state A and its temperature as T. Let the internal energy of the system in state A be called UA. We can change the state of the system in two different ways. 2019 to 20. Thermodynamics 163. One way. We do some mechanical work, say 1 kg, by rotating a set of small paddles and thereby churning water. Let the new state be called B state and its temperature as Tb. It is found that Tb, Ta and the change in temperature, T is equal to Tb Ta. Let the internal energy of the system in state B be Ub and the change in internal energy, U is equal to Ub Ua. Second way, we now do an equal amount, i.e., 1 kg, electrical work with the help of an immersion rod and note down the temperature change. We find that the change in temperature is same as in the earlier case, say, Tb Ta. In fact, the experiments in the above manner were done by J.P. Joule between 1840-50 and he was able to show that a given amount of work done on the system, no matter how it was done, irrespective of path, produced the same change of state, as measured by the change in the temperature of the system. So, it seems appropriate to define a quantity, the internal energy U, whose value is characteristic of the state of a system, whereby the adiabatic work, WAD required to bring about a change of state is equal to the difference between the value of U in one state and that in another state, U i.e. 1 add is equal to WU. Therefore, internal energy, U, of the system is a state function. By conventions of IPAC in chemical thermodynamics, the positive sign expresses that WAD is positive when work is done on the system and the internal energy of system increases. Similarly, if the work is done by the system, WAD will be negative because internal energy of the system decreases. Can you name some other familiar state functions? Some of other familiar state functions are V, P, and T. For example, if we bring a change in temperature of the system from 25 degrees Celsius to 35 degrees Celsius, The change in temperature is 35 degrees C. 25 degrees C is equal to plus 10 degrees Celsius. Whether we go straight up to 35 degrees Celsius or we cool the system for a few degrees, then take the system to the final temperature. Thus, T is a state function and the change in temperature is independent of the route taken. Volume of water in a pond, for example, is a state function, because change in volume of its water is independent of the route by which water is filled in the pond, either by rain or by tubule or by both. B. Heat. We can also change the internal energy of a system by transfer of heat from the surroundings to the system or vice versa without expenditure of work. This exchange of energy, which is a result of temperature difference, is called heat, Q. Let us consider bringing about the same change in temperature, the same initial and final states as before in section 6 January 2004, A. By transfer of heat through thermally conducting walls instead of adiabatic walls, Fig 6.4. We take water at temperature Ta in a container having thermally conducting walls, say made up of copper, and enclose it in a huge heat reservoir at temperature Tb. The heat absorbed by the system, water, Q, can be measured in terms of temperature difference, Tβ. In this case, change in internal energy, U, is equal to Q, when no work is done at constant volume. By conventions of IIT in chemical thermodynamics, the Q is positive when heat is transferred from the surroundings to the system and the internal energy of the system increases, and Q is negative when heat is transferred from system to the surroundings, resulting in decrease of the internal energy of the system. Earlier negative sign was assigned when the work is done on the system and positive sign when the work is done by the system. This is still followed in physics books, although IIT has recommended the use of new sign convention. Fig. 6.4, a system which allows heat transfer through its boundary. 2019-20. Chemistry 164, C. The general case. Let us consider the general case in which a change of state is brought about both by doing work and by transfer of heat. We write change in internal energy for this case as U is equal to Q plus W. 6.1. For a given change in state, Q and W can vary depending on how the change is carried out. However, Q plus W is equal to U will depend only on initial and final state. It will be independent of the way the change is carried out. If there is no transfer of energy as heat or as work, isolated system, i.e., if W is equal to 0 and Q is equal to 0, then U is equal to 0. The equation 6.1, i.e., U is equal to Q plus W is mathematical statement of the first law of thermodynamics, which states that the energy of an isolated system is constant. It is commonly stated as the law of conservation of energy, i.e., energy can neither be created nor be destroyed. Note, there is considerable difference between the character of the thermodynamic property energy and that of a mechanical property such as volume. We can specify an unambiguous, absolute value for volume of a system in a particular state, but not the absolute value of the internal energy. However, we can measure only the changes in the internal energy, U, of the system. Problem 6.1 express the change in internal energy of a system when I. No heat is absorbed by the system from the surroundings, but work, W, is done on the system. What type of wall does the system have? 2. No work is done on the system, but Q amount of heat is taken out from the system and given to the surroundings. What type of wall does the system have? 3. W amount of work is done by the system and Q amount of heat is supplied to the system. What type of system would it be? Solution: I. U is equal to W add. Wall is adiabatic. 2. U is equal to Q. Thermally conducting walls. 3. U is equal to QW. Closed system. 6.2 Applications. Many chemical reactions involve the generation of gases capable of doing mechanical work or the generation of heat. It is important for us to quantify these changes and relate them to the changes in the internal energy. Let us see how. 6th February 2001 Work. First of all, let us concentrate on the nature of work a system can do. We will consider only mechanical work, i.e., pressure volume work. For understanding pressure volume work, let us consider a cylinder which contains 1 mole of an ideal gas fitted with a frictionless piston. Total volume of the gas is 6 and pressure of the gas inside is P. If external pressure is Px, which is greater than P, piston is moved inward till the pressure inside becomes equal to Px. Let this change Fig. 6.5 a. Work done on an ideal gas in a cylinder when it is compressed by a constant external pressure, Px, in single step, is equal to the shaded area. 2019-20. Thermodynamics 165 be achieved in a single step and the final volume BVF. During this compression, suppose piston moves a distance, L and is cross-sectional area of the piston is A, Fig. 6.5, A. Then, volume change is equal to L times A is equal to V is equal to VF6. We also know, force pressure area is equal to therefore, force on the piston is equal to Px. If W is the work done on the system by movement of the piston, then W is equal to force times distance is equal to Px. L is equal to Px. V is equal to Px. V is equal to Px. VF6, 6.2. The negative sign of this expression is required to obtain conventional sign for W, which will be positive. It indicates that in case of compression work is done on the system. Here, VF6 will be negative and negative multiplied by negative will be positive. Hence the sign obtained for the work will be positive. If the pressure is not constant at every stage of compression, but changes in number of finite steps, work done on the gas will be summed over all the steps and will be equal to PV. Fig. 6.5, b. If the pressure is not constant but changes during the process such that it is always infinitesimally greater than the pressure of the gas, then, at each stage of compression, the volume decreases by an infinitesimal amount, dV. In such a case we can calculate the work done on the gas by the relation W is equal to P dV x VVIF. 6.3. Here, Px at each stage is equal to Pin plus dP. In case of compression, Fig. 6.5, c. In an expansion process under similar conditions, the external pressure is always less than the pressure of the system, i.e., Px is equal to Pin dP. In general case we can write Px is equal to Pin plus dP. Such processes are called reversible processes. A process or change is said to be reversible if a change is brought out in such a way that the process could, at any moment, be reversed by an infinitesimal change. A reversible process proceeds infinitely slowly by a series of equilibrium states such that system and the surroundings are always in near equilibrium with each other. Processes Fig. 6.5, c. PV plot when pressure is not constant and changes in infinite steps, reversible conditions, during compression from initial volume, 6 to final volume, Vf. Work done on the gas is represented by the shaded area. Fig. 6.5, b. PV plot when pressure is not constant and changes in finite steps during compression from initial volume, 6 to final volume, Vf. Work done on the gas is represented by the shaded area. 2019-20. Chemistry 166. Other than reversible processes are known as irreversible processes. In chemistry, we face problems that can be solved if we relate the work term to the internal pressure of the system. We can relate work to internal pressure of the system under reversible conditions by writing equation 6.3 as follows. Rev x v v v v p d v p d p d v I f is equal to plus or minus. In since dp times dv is very small, we can write rev v v d I f is equal to pv in 6.4. Now, the pressure of the gas, Pin, which we can write as P now, can be expressed in terms of its volume through gas equation. For n mole of an ideal gas, i.e., PV is equal to nRT is equal to PTV nR. Therefore, at constant temperature, isothermal process, Rev is equal to NNR RT dVVT VVF for VIF ln is equal to 2.303 nRT log VVFI. 6.5. Free expansion. Expansion of a gas in vacuum, Px is equal to 0, is called free expansion. No work is done during free expansion of an ideal gas, whether the process is reversible or irreversible. Equation 6.2 and 6.3. Now, we can write equation 6.1 in number of ways depending on the type of processes. Let us substitute W is equal to Pxv, x 6.2, in equation 6.1. And we get UQPV x is equal to, if a process is carried out at constant volume, V is equal to 0, then U is equal to QV. The subscript V in QV denotes that heat is supplied at constant volume. Isothermal and free expansion of an ideal gas. For isothermal, T is equal to constant, expansion of an ideal gas into vacuum, W is equal to 0 since Px is equal to 0. Also, Joule determined experimentally that Q is equal to 0, therefore, U is equal to 0. Equation 6.1, W is equal to plus U can be expressed for isothermal, irreversible and reversible changes as follows. 1. For isothermal irreversible change, Q is equal to W is equal to Px, Vf6. 2. For isothermal reversible change, Q is equal to W is equal to nRT ln FIVV is equal to 2.303 nRT log VVFI. 3. For adiabatic change, Q is equal to 0. U is equal to Watt. Problem 6.22 liters of an ideal gas at a pressure of 10 atm expands isothermally at 25 degrees Celsius into a vacuum until its total volume is 10 liters. How much heat is absorbed and how much work is done in the expansion? Solution: we have Q is equal to W is equal to Px, 10 2 is equal to 0, 8 is equal to 0. Number work is done, no heat is absorbed. Problem 6.3. Consider the same expansion, but this time against a constant external pressure of 1 atm. Solution: we have Q is equal to W is equal to Px, 8 is equal to 8 liter atm. Problem 6.4. Consider the expansion given in problem 6.2. For 1 mole of an ideal gas conducted reversibly. Solution: we have Q is equal to W is equal to 2.303 nRT log VVFS is equal to 2.303 times 1 times 0.8206 times 298 times log 10 to 2019 to 20. Thermodynamics 167 is equal to 2.303 x 0.8206 x 298 x log 5 is equal to 2.303 x 0.8206 x 298 x 0.6990 is equal to 393.66 LATM. Remember, H is equal to QP, heat absorbed by the system at constant pressure. H is negative for exothermic reactions which evolve heat during the reaction, and H is positive for endothermic reactions which absorb heat from the surroundings. At constant volume, V is equal to 0, U is equal to QV. Therefore equation 6.8 becomes H is equal to U is equal to QV. The difference between H and U is not usually significant for systems consisting of only solids and or liquids. Solids and liquids do not suffer any significant volume changes upon heating. The difference, however, becomes significant when gases are involved. Let us consider a reaction involving gases. If V is the total volume of the gaseous reactants, Vb is the total volume of the gaseous products, Na is the number of moles of gaseous reactants, and Nb is the number of moles of gaseous products, all at constant pressure and temperature, then using the ideal gas law, we write PVA is equal to NART and PVB is equal to NBRT. Thus, PVB PVA is equal to NBRT, NART is equal to NB Na, RT or P, VB V is equal to NB Na, RT or PV is equal to NGRT. 6.9. Here, Ng refers to the number of moles of gaseous products minus the number of moles of gaseous reactants. Substituting the value of PV from equation 6.9 in equation 6.8, we get H is equal to U plus NGRT. 6.10. The equation 6.10 is useful for calculating H from U and vice versa. Problem 6.5. If water vapor is assumed to be a perfect gas, molar enthalpy change for vaporization of 1 mole of water at 1 bar and 100 degrees Celsius is 41 kJ mol 1. Calculate the internal energy change when 6 February 2002. Enthalpy, H, a useful new state function. We know that the heat absorbed at constant volume is equal to change in the internal energy, i.e., U is equal to QV. But most of chemical reactions are carried out not at constant volume, but in flasks or test tubes under constant atmospheric pressure. We need to define another state function which may be suitable under these conditions. We may write equation 6.1 as U is equal to QPPV at constant pressure, where QP is heat absorbed by the system and PV represent expansion work done by the system. Let us represent the initial state by subscript 1 and final state by 2. We can rewrite the above equation as U2 U1 is equal to QPP, V2 V1. On rearranging, we get QP is equal to U2 plus PV2, U1 plus PV1. 6.6. Now we can define another thermodynamic function, the enthalpy H, Greek word enthalpine, to warm or heat content, as H is equal to U plus PV. 6.7. So, equation 6.6 becomes QP is equal to H2 H1 is equal to H. Although Q is a path-dependent function, H is a state function because it depends on U, P and V, all of which are state functions. Therefore, H is independent of path. Hence, QP is also independent of path. For finite changes at constant pressure, we can write equation 6.7 as H is equal to U plus PV. Since P is constant, we can write H is equal to U plus PV. 6.8. It is important to note that when heat is absorbed by the system at constant pressure, We are actually measuring changes in the enthalpy, 2019 to 20. Chemistry 1681 mole of water is vaporized at 1 bar pressure and 100 degrees Celsius. Solution, I. The change, 2 to HOHOGLR is equal to plus GHUNT or U is equal to HNTGR. Substituting the values, we get U is equal to times 41,001,833,173,111. kJ mol J mol Kk is equal to 41.00 kJ mol 13.096 kJ mol 1 is equal to 37.904 kJ mol 1. B. Extensive and intensive properties in thermodynamics. A distinction is made between extensive properties and intensive properties. An extensive property is a property whose value depends on the quantity or size of matter present in the system. For example, mass, volume, internal energy, enthalpy, heat capacity, etc. are extensive properties. Those properties which do not depend on the quantity or size of matter present are known as intensive properties. For example, temperature, density, pressure, etc. are intensive properties. A molar property, Km, is the value of an extensive property Ki of the system for 1 mole of the substance. If N is the amount of matter, Km is equal to N is independent of the amount of matter. Other examples are molar volume, Vm, and molar heat capacity, Cm. Let us understand the distinction between extensive and intensive properties by considering a gas enclosed in a container of volume V and at temperature T, Fig 6.6, a. Let us make a partition such that volume is halved. Each part, Fig 6.6, B, now has 1/2 of the original volume, V2, but the temperature will still remain the same, i.e., T. It is clear that volume is an extensive property and temperature is an intensive property. See heat capacity in this subsection. Let us see how to measure heat transferred to a system. This heat appears as a rise in temperature of the system in case of heat absorbed by the system. The increase of temperature is proportional to the heat transferred. Q coeft is equal to times the magnitude of the coefficient depends on the size, composition and nature of the system. We can also write it as Q is equal to Ct. The coefficient, C, is called the heat capacity. Thus, we can measure the heat supplied by monitoring the temperature rise, provided we know the heat capacity. When C is large, a given amount of heat results in only a small temperature rise. Water has a large heat capacity, i.e., a lot of energy is needed to raise its temperature. C is directly proportional to amount of substance. The molar heat capacity of a substance, Cm is equal to Cn, is the heat capacity for 1 mole of the substance and is the quantity of heat needed to raise the temperature of 1 mole by 1 degree Celsius, or 1 Kelvin. Specific heat, also called specific heat capacity, is the quantity of heat required to raise the temperature of 1 unit mass of a Fig. 6.6, a gas at volume V and temperature T. Fig. 6.6, B. Partition, each part having half the volume of the gas. 2019 to 20. Thermodynamics 169 substance by 1 degree Celsius, or 1 Kelvin. For finding out the heat, Q, required to raise the temperatures of a sample, we multiply the specific heat of the substance, C, by the mass m, and temperatures change, T as QCMT. Ct is equal to times is equal to 6.11 d. the relationship between Cp and Cv for an ideal gas at constant volume, the heat capacity, C is denoted by Cv, and at constant pressure, this is denoted by Cp. Let us find the relationship between the two. We can write equation for heat, Q at constant volume as Qv is equal to Ctu, V is equal to at constant pressure as Qp is equal to Ct, Hp is equal to the difference between Cp and Cv can be derived for an ideal gas as, for a mole of an ideal gas, H is equal to U plus, Pv is equal to U plus, RT is equal to U plus RT is equal to plus HUTR, 6.12. On putting the values of H and U, we have CTTPV is equal to plus R, CCPV is equal to plus R, CPCV is equal to R, 6.13. 6.3 Measurement of U and H calorimetry. We can measure energy changes associated with chemical or physical processes by an experimental technique called calorimetry. In calorimetry, the process is carried out in a vessel called calorimeter, which is immersed in a known volume of a liquid. Knowing the heat capacity of the liquid in which calorimeter is immersed and the heat capacity of calorimeter, it is possible to determine the heat evolved in the process by measuring temperature changes. Measurements are made under two different conditions, I, at constant volume, QV2, at constant pressure, Qp, I, U. Measurements for chemical reactions, heat absorbed at constant volume, is measured in a bomb calorimeter, Fig. 6.7. Here, a steel vessel, the bomb, is immersed in a water bath. The whole device is called calorimeter. The steel vessel is immersed in water bath to ensure that no heat is lost to the surroundings. A combustible substance is burned in pure dioxygen supplied Fig. 6.7 bomb calorimeter in the steel bomb. Heat evolved during the reaction is transferred to the water around the bomb and its temperature is monitored. Since the bomb calorimeter is sealed, its volume does not change, i.e., the energy changes associated with reactions are measured at constant volume. Under these conditions, no work is done as the reaction is carried out at constant volume in the bomb calorimeter. Even for reactions involving gases, there is no work done as V is equal to 0. Temperature change of the calorimeter produced by the completed reaction is then converted to QV, by using the known heat capacity of the calorimeter with the help of equation 6.11. 2019-20. Chemistry 170, B. H. Measurements. Measurement of heat change at constant pressure, generally under atmospheric pressure, can be done in a calorimeter shown in Fig. 6.8. We know that eta is equal to Qp, at constant P, and, therefore, heat absorbed or evolved, Qp at constant pressure is also called the heat of reaction or enthalpy of reaction, RH. In an exothermic reaction, heat is evolved, and system loses heat to the surroundings. Therefore, Qp will be negative and RH will also be negative. Similarly, in an endothermic reaction, heat is absorbed, Qp is positive and RH will be positive. Problem 6.61 G of graphite is burned in a bomb calorimeter in excess of oxygen at 298 K and 1 atmospheric pressure according to the equation C, graphite, plus O2, G, CO2, G. During the reaction, temperature rises from 298 K to 299 K. If the heat capacity Fig. 6.8 calorimeter for measuring heat changes at constant pressure, atmospheric pressure, of the bomb calorimeter is 20.7 kJK, what is the enthalpy change for the above reaction at 298 K and 1 atm? Solution. Suppose Q is the quantity of heat from the reaction mixture and Cv is the heat capacity of the calorimeter, then the quantity of heat absorbed by the calorimeter. Q is equal to Cv times T. Quantity of heat from the reaction will have the same magnitude but opposite sign because the heat lost by the system, reaction mixture, is equal to the heat gained by the calorimeter. QCTV is equal to kJ times is equal to 27 299 298 27. Here, negative sign indicates the exothermic nature of the reaction, thus, U for the combustion of the 1 g of graphite is equal to 20.7 kJ. 1 for combustion of 1 mole of graphite is equal to mol 12.02711. G kg times is equal to 2.48 times 102 kg mol 1, since Ng is equal to 0. H is equal to U is equal to 2.48 times 102 kg mol 16.4. Enthalpy change, RH of a reaction. Reaction enthalpy in a chemical reaction, reactants are converted into products and is represented by reactants products. The enthalpy change accompanying a reaction is called the reaction enthalpy. The enthalpy change of a chemical reaction is given by the symbol RH. RH is equal to sum of enthalpies of products, sum of enthalpies of reactants, is equal to I products I reactants to HBH. 6.14. Here symbol, sigma, is used for summation and I and by are the stoichiometric 2019-20. Thermodynamics 171 coefficients of the products and reactants respectively in the balanced chemical equation. For example, for the reaction CH4, G, plus 2O2, G, CO2, G, plus 2H2O, L, RII products II react TSHAHBH is equal to PR tan is equal to HM, CO2G, plus 2HM, H2O, L, HM, CH4, G, plus 2HM, O2G, where HM is the molar enthalpy. Enthalpy change is a very useful quantity. Knowledge of this quantity is required when one needs to plan the heating or cooling required to maintain an industrial chemical reaction at constant temperature. It is also required to calculate temperature dependence of equilibrium constant. I. Standard enthalpy of reactions. Enthalpy of a reaction depends on the conditions under which a reaction is carried out. It is, therefore, necessary that we must specify some standard conditions. The standard enthalpy of reaction is the enthalpy change for a reaction when all the participating substances are in their standard states. The standard state of a substance at a specified temperature is its pure form at 1 bar. For example, the standard state of liquid ethanol at 298 K is pure liquid ethanol at 1 bar. Standard state of solid iron at 500 K is pure iron at 1 bar. Usually data are taken at 298 K. Standard conditions are denoted by adding the superscript to the symbol H, e.g., H, B. Enthalpy changes during phase transformations. Phase transformations also involve energy changes. Ice, for example, requires heat for melting. Normally this melting takes place at constant pressure, atmospheric pressure, and during phase change, temperature remains constant, at 273 K. H2O, S, H2O, L, Fusage is equal to 6.00 kJ mol 1. Here fusage is enthalpy of fusion in standard state. If water freezes, then process is reversed and equal amount of heat is given off to the surroundings. The enthalpy change that accompanies melting of 1 mole of a solid substance in standard state is called standard enthalpy of fusion or molar enthalpy of fusion, FUSH. Melting of a solid is endothermic, so all enthalpies of fusion are positive. Water requires Table 6.1 standard enthalpy changes of fusion and vaporization. TF and TB are melting and boiling points, respectively, 2019 to 20. Chemistry 172 Heat for evaporation. At constant temperature of its boiling point Tb and at constant pressure, H2O, L, H2O, G, VapH is equal to plus 40.79 kJ mol. 1 VapH is the standard enthalpy of vaporization. Amount of heat required to vaporize 1 mole of a liquid at constant temperature and under standard pressure, 1 bar, is called its standard enthalpy of vaporization or molar enthalpy of vaporization, VapH. Sublimation is direct conversion of a solid into its vapor. Solid CO2 or dry ice sublimes at 195 K with subH is equal to 25.2 kJ mol 1. Naphthalene sublimes slowly and for this subH is equal to 73.0 kJ mol 1. Standard enthalpy of sublimation. SubH is the change in enthalpy when 1 mole of a solid substance sublimes at a constant temperature and under standard pressure, 1 bar. The magnitude of the enthalpy change depends on the strength of the intermolecular interactions in the substance undergoing the phase transformations. For example, the strong hydrogen bonds between water molecules hold them tightly in liquid phase. For an organic liquid, such as acetone, the intermolecular dipole-dipole interactions are significantly weaker. Thus, it requires less heat to vaporize 1 mole of acetone than it does to vaporize 1 mole of water. Table 6.1 gives values of standard enthalpy changes of fusion and vaporization for some substances. Problem 6.7 A swimmer coming out from a pool is covered with a film of water weighing about 18 g. How much heat must be supplied to evaporate this water at 298 K? Calculate the internal energy of vaporization at 298 K. VapH for water at 298 K is equal to 44.01 kJ mol 1 solution. We can represent the process of evaporation as HO, G. 1 mol 2 vaporization 21 no of moles in 18 G H2O, L, is 118 G 1 mol 18 G mole is equal to heat supplied to evaporate 18 G water at 298 K is equal to N times VapH is equal to 1 mol times 44.01 kJ mol 1 is equal to 44.01 kJ. Assuming steam behaving as an ideal gas is equal to vap GUHPVH nRT VapHTV is equal to nRJK mol kg 4401 18314 298 10th November 1931 kj vap UV is equal to 44 1st February 1948 4153 kj Problem 6.8 Assuming the water vapor to be a perfect gas, calculate the internal energy change when 1 mole of water at 100 degrees Celsius and 1 bar pressure is converted to ice at 0 degrees C. Given the enthalpy of fusion of ice is 6.00 kJ mol 1 heat capacity of water is 4.2 jg degree C. The change take place as follows. Step 1 1 mol H2O, L, 100 degrees Celsius, 1 mol, L, 0 degrees C, enthalpy change H1 Step 2 1 mol H2O, L, 0 degrees C, 1 mol H2O, S, 0 degrees C, enthalpy change H2 total enthalpy change will be H is equal to H1 plus H2. H1 is equal to 18x4.2 x 100, J mol 1 is equal to 7560 J mol 1 is equal to 7.56 kJ mol 1. H2 is equal to 6.00 kJ mol 1. 2019 to 20. Thermodynamics 173 aggregation, also known as reference states, is called standard molar enthalpy of formation. Its symbol is FH, where the subscript F indicates that 1 mole of the compound in question has been formed in its standard state from its elements in their most stable states of aggregation. The reference state of an element is its most stable state of aggregation at 25 degrees Celsius and 1 bar pressure. For example, the reference state of the hydrogen is H2 gas and those of dioxygen, carbon and sulfur are O2 gas, graphite and rhombic respectively. Some reactions with standard molar enthalpies of formation are as follows. Table 6.2 Standard molar enthalpies of formation, FH, at 298 K of a few selected substances. Therefore, H is equal to 7.56 kJ mol 1 plus 6.00 kJ mol 1 is equal to 13.56 kJ mol 1. There is negligible change in the volume during the change from liquid to solid state. Therefore, PV is equal to NGRT is equal to 0. H is equal to U is equal to 13.56 kJ mol 1. C. Standard enthalpy of formation. The standard enthalpy change for the formation of 1 mole of a compound from its elements in their most stable states of 2019 to 20. Chemistry 174H2, G, plus half O2, G, H2O, 1, FH is equal to 285.8 kJ mol 1 C, graphite, S, plus 2H2, G, CH4, G, FH is equal to 74.81 kJ mol 1 2 C, graphite, S, plus 3H2, G, plus half O2, G, C2H5O, 1, FH is equal to 277.7 kJ mol 1. It is important to understand that a standard molar enthalpy of formation, FH, is just a special case of RH, where 1 mole of a compound is formed from its constituent elements, as in the above 3 equations, where 1 mole of each, water, methane and ethanol is formed. In contrast, the enthalpy change for an exothermic reaction, CaO, S, plus CO2, G, CaO3, S, RH is equal to 178.3 kJ mol 1 is not an enthalpy of formation of calcium carbonate, since calcium carbonate has been formed from other compounds, and not from its constituent elements. Also, for the reaction given below, enthalpy change is not standard enthalpy of formation, FH for HBr, G, H2, G, plus Br2, L, 2HBr, G, RH is equal to 178.3 kJ mol 1. Here 2 moles, instead of 1 mole of the product is formed from the elements, i.e. RH is equal to 2FH. Therefore, by dividing all coefficients in the balanced equation by 2, expression for enthalpy of formation of HBr, G, is written as half H2, G, plus half Br2, 1, HBr, G, FH is equal to 36.4 kJ mol 1. Standard enthalpies of formation of some common substances are given in table 6.2. By convention, standard enthalpy for formation, FH, of an element in reference state, i.e., its most stable state of aggregation is taken as 0. Suppose, You are a chemical engineer and want to know how much heat is required to decompose calcium carbonate to lime and carbon dioxide, with all the substances in their standard state. CaCO3, S, CaO, S, plus CO2, G, RH is equal to. Here, we can make use of standard enthalpy of formation and calculate the enthalpy change for the reaction. The following general equation can be used for the enthalpy change calculation. RH is equal to IIFH, products, I by FH, reactants, 6.15, where A and B represent the coefficients of the products and reactants in the balanced equation. Let us apply the above equation for decomposition of calcium carbonate. Here, coefficients A and B are 1 each. Therefore, RH is equal to FH is equal to CaO, S, plus FH, CO2, G. FH is equal to CaCO3, S, is equal to 1635.1 kg mol 1, plus 1393.5 kg mol 1, 1206.9 kg mol 1, is equal to 178.3 kg mol 1. Thus, the decomposition of CaCO3, S, is an endothermic process and you have to heat it for getting the desired products. D. Thermochemical equations. A balanced chemical equation together with the value of its RH is called a thermochemical equation. We specify the physical state, along with allotropic state, of the substance in an equation. For example, C2H5O, L, plus 3O2, G, 2CO2, G, plus 3H2O, L, RH is equal to 1367 kg mol 1. The above equation describes the combustion of liquid ethanol at constant temperature and pressure. The negative sign of enthalpy change indicates that this is an exothermic reaction. It would be necessary to remember the following conventions regarding thermochemical equations. 1. The coefficients in a balanced thermochemical equation refer to the number of moles, never molecules, of reactants and products involved in the reaction. 2. The numerical value of RH refers to the number of moles of substances specified by an equation. Standard enthalpy change RH will have units as kg mol 1. 2019-20. Thermodynamics 175. To illustrate the concept, let us consider the calculation of heat of reaction for the following reaction: FeOSHG FeSHOL 23-22323 plus from the table 6.2 of standard enthalpy of formation FH, we find FH H2OL is equal to 285.83 kg mol 1, FH Fe2O3S is equal to 824.2 kg mol 1, also FH Fe S is equal to 0 and FH H2G is equal to 0 as per convention. Then FH1 is equal to 285.83 kg mol 1, 824.2 kg mol 1 is equal to 857.5 plus 824.2 kg mol 1 is equal to 33.3 kg mol 1. Note that the coefficients used in these calculations are pure numbers, which are equal to the respective stoichiometric coefficients. The unit for RH is kg mol 1, which means per mole of reaction. Once we balance the chemical equation in a particular way, as above, this defines the mole of reaction. If we had balanced the equation differently, for example, 1232322 FeOSHG FeSHOL plus then this amount of reaction would be 1 mole of reaction and RH would be FH2 is equal to 32285.83 kJ mol 1, 12824.2 kJ mol 1 is equal to 428.7 plus 412.1 kJ mol 1 is equal to 16.6 kJ mol 1 is equal to a half RH1. It shows that enthalpy is an extensive quantity. 3. When a chemical equation is reversed, the value of RH is reversed in sign. For example, N2 G plus 3H2 G 2NH3 G RH is equal to 91.8 kJ mol 1 2NH3 G N2 G plus 3H2 G RH is equal to plus 91.8 kJ mol 1. E. Hess's law of constant heat summation. We know that enthalpy is a state function, therefore the change in enthalpy is independent of the path between initial state, reactants, and final state, products. In other words, enthalpy change for a reaction is the same whether it occurs in one step or in a series of steps. This may be stated as follows in the form of Hess's law. If a reaction takes place in several steps, then its standard reaction enthalpy is the sum of the standard enthalpies of the intermediate reactions into which the overall reaction may be divided at the same temperature. Let us understand the importance of this law with the help of an example. Consider the enthalpy change for the reaction C, graphite S, plus 12O2, G, Co, G, RH is equal to. Although Co, G, is the major product, some CO2 gas is always produced in this reaction. Therefore, we cannot measure enthalpy change for the above reaction directly. However, if we can find some other reactions involving related species, it is possible to calculate the enthalpy change for the above reaction. Let us consider the following reactions: C, graphite S, plus O2, G, CO2, G, RH is equal to 393.5 kJ mol 1, I, Co, G, plus 12O2, G, CO2, G, RH is equal to 283.0 kJ mol 1, 2. We can combine the above two reactions in such a way so as to obtain the desired reaction. To get 1 mole of Co, G, on the right, we reverse equation 2. In this, heat is absorbed instead of being released, so we change sign of RH value CO2, G, Co, G, plus 12O2, G, RH is equal to plus 283.0 kJ mol 1, 3, 2019 to 20. Chemistry 176. Adding equation I and 3, we get the desired equation C graphite SOG Co G plus 122 for which RH is equal to 393.5 plus 283.0 is equal to 110.5 kJ mol 1. In general, if enthalpy of an overall reaction AB along one route is RH and RH1, RH2, RH3, representing enthalpies of reactions leading to same product, B along another route, then we have RH is equal to RH1 plus RH2 plus RH3. 6.16, it can be represented as 6.5 enthalpies for different types of reactions. It is convenient to give name to enthalpies specifying the types of reactions. A. Standard enthalpy of combustion, symbol CH. Combustion reactions are exothermic in nature. These are important in industry, rocketry, and other walks of life. Standard enthalpy of combustion is defined as the enthalpy change per mole, or per unit amount, of a substance, when it undergoes combustion and all the reactants and products being in their standard states at the specified temperature. Cooking gas in cylinders contains mostly butane, C4H10. During complete combustion of 1 mole of butane, 2658 kJ of heat is released. We can write the thermochemical reactions for this as CHGOG-COGHO410 to 2nd February 2013 2451 plus CH is equal to 2658.0 kJ mol 1. Similarly, combustion of glucose gives out 2802.0 kJ mol of heat, for which the overall equation is CHOGOG-612-622-66661 plus CH is equal to 2802.0 kJ mol 1. Our body also generates energy from food by the same overall process as combustion, although the final products are produced after a series of complex biochemical reactions involving enzymes. ABCDH1 RH2 RH3 RH. Problem 6.9. The combustion of 1 mole of benzene takes place at 298 K and 1 atm. After combustion, CO2, G, and H2O, 1, are produced and 3267.0 kJ of heat is liberated. Calculate the standard enthalpy of formation, FH of benzene. Standard enthalpies of formation of CO2, G, and 2HO, L, are 393.5 kJ mol 1 and 285.83 kJ mol 1 respectively. Solution. The formation reaction of benzene is given by 3rd February 1966 C graphite HgCHl plus FH is equal to I. The enthalpy of combustion of 1 mole of benzene is CHLO-COGHOL 66 to 2nd February 2015 263 plus CH is equal to 3267 kJ mol 1. 2. The enthalpy of formation of 1 mole of CO2, G, C graphite OG plus 2 FH is equal to 393.5 kJ mol 1. 3. The enthalpy of formation of 1 mole of H2O, L, is HgOgHOl 22212 plus CH is equal to 285.83 kJ mol 1. 4. Multiplying EGNA 3 by 6 and EGNA 4 by 3 we get 2019 to 20. Thermodynamics 177 666 22 C graphite OG plus FH is equal to 2361 kJ mol 1332 312 22 HgOgHO plus FH is equal to 857.49 kJ mol 1. Summing up the above two equations, 6th March 2015 2632222 C graphite HgOgHOl plus FH is equal to 3218.49 kJ mol 1. We, reversing equation, 2. 6315 22nd February 1966 2 COGHOL plus FH is equal to 3267.0 kJ mol 1. 6. Adding equations, we, and 6, we get 3rd February 1966 C graphite HgCHl plus FH is equal to 48.51 kJ mol 1. 4. In this case, the enthalpy of atomization is same as the enthalpy of sublimation. C. Bond enthalpy, symbol, bond H, Chemical reactions involve the breaking and making of chemical bonds. Energy is required to break a bond and energy is released when a bond is formed. It is possible to relate heat of reaction to changes in energy associated with breaking and making of chemical bonds. With reference to the enthalpy changes associated with chemical bonds, two different terms are used in thermodynamics. I. Bond dissociation enthalpy. 2. Mean bond enthalpy. Let us discuss these terms with reference to diatomic and polyatomic molecules. Diatomic molecules. Consider the following process in which the bonds in 1 mole of the hydrogen gas, H2, are broken, H2, G, 2H, G. HHH is equal to 435.0 kJ/mol 1. The enthalpy change involved in this process is the bond dissociation enthalpy of HH bond. The bond dissociation enthalpy is the change in enthalpy when 1 mole of covalent bonds of a gaseous covalent compound is broken to form products in the gas phase. Note that it is the same as the enthalpy of atomization of the hydrogen. This is true for all diatomic molecules. For example, Cl2, G, 2Cl, G, ClClH is equal to 242 kJ/mol 1 O2, G, 2O, G, O is equal to 428 kJ/mol 1. In the case of polyatomic molecules, bond dissociation enthalpy is different for different bonds within the same molecule. Polyatomic molecules. Let us now consider a polyatomic molecule like methane, CH4. The overall thermochemical equation for its atomization reaction is given below. CHGCgHg44 plus AH is equal to 1665 kJ/mol 1. In methane, all the 4 CH bonds are identical in bond length and energy. However, the energies required to break the individual CH bonds in each successive step differ. B. Enthalpy of atomization, symbol, AH. Consider the following example of atomization of the hydrogen H2, G, 2H, G. AH is equal to 435.0 kJ/mol 1. You can see that H atoms are formed by breaking HH bonds in the hydrogen. The enthalpy change in this process is known as enthalpy of atomization, AH. It is the enthalpy change on breaking 1 mole of bonds completely to obtain atoms in the gas phase. In case of diatomic molecules, like the hydrogen, given above, the enthalpy of atomization is also the bond dissociation enthalpy. The other examples of enthalpy of atomization can be CH4, G, C, G, plus 4H, G. AH is equal to 1665 kJ/mol 1. Note that the products are only atoms of C and H in gaseous phase. Now see the following reaction, Na, S, Na, G. AH is equal to 108.4 kJ/mol 1. 2019-20. Chemistry 178 CH4, G, CH3, G, plus H, G, bond H is equal to plus 427 kJ/mol 1. CH3, G, CH2, G, plus H, G, bond H is equal to plus 439 kJ/mol 1. CH2, G, CH, G, plus H, G, bond H is equal to plus 452 kJ/mol 1. CH, G, C, G, plus H, G, bond H is equal to plus 347 kJ/mol 1. Therefore, CH4, G, C, G, plus 4H, G, AH is equal to 1665 kJ/mol 1. In such cases, we use mean bond enthalpy of CH bond. For example, in CH4, CHH is calculated as CHH is equal to a quarter, AH is equal to a quarter, 1665 kgmol 1 is equal to 416 kgmol 1. We find that mean CH bond enthalpy in methane is 416 kgmol. It has been found that mean CH bond enthalpies differ slightly from compound to compound, as in CH3 CH2 Cl CH3 NO2, etc., but it does not differ in a great deal. Using Hess's law, bond enthalpies can be calculated. Bond enthalpy values of some single and multiple bonds are given in table 6.3. The reaction enthalpies are very important quantities as these arise from the changes that accompany the breaking of old bonds and formation of the new bonds. We can predict enthalpy of a reaction in gas phase if we know different bond enthalpies. The standard enthalpy of reaction, RH, is related to bond enthalpies of the reactants and products in gas phase reactions as RH is equal to bond enthalpies reactants products 6.17 ***. This relationship is particularly more useful when the required values of FH are not available. The net enthalpy change of a reaction is the amount of energy required to break all the bonds in the reactant molecules minus the amount of energy required to break all the bonds in the product molecules. Remember that this relationship is HCNOF SCLBRI 435.8 414 389 464 569 293 318 339 431 368 297 H34729 351 439 289 264 259 330 276 238 C159 201 272 to 209 201 243 N13818 368 351 to 205 201 0155540 490 327 255 197 F176 213 226 360 289 213 Psi 213 331 272 213 P213 213 S243 209 close 192 180 BR 151 I table 6.3 I. Some mean single bond enthalpies in kgmol 1 at 298 Kn is equal to N418 C is equal to C611 O is equal to O498 N946 CC837 C is equal to N615 C is equal to O741 C N891 CO 1070. Table 6.3 B. Some mean multiple bond enthalpies in kgmol 1 at 298 K ***. If we use enthalpy of bond formation, F bond, which is the enthalpy change when 1 mole of a particular type of bond is formed from gaseous atom, then FH is equal to FH bonds of products, FH bonds of reactants **. Note that symbol used for bond dissociation enthalpy and mean bond enthalpy is the same. 2019 to 20. Thermodynamics 179 approximate and is valid when all substances, reactants and products in the reaction are in gaseous state. D. Lattice enthalpy. The lattice enthalpy of an ionic compound is the enthalpy change which occurs when 1 mole of an ionic compound dissociates into its ions in gaseous state. NaCl(S) NaGCl(G++) plus lattice H is equal to plus 788 kJ/mol1. Since it is impossible to determine lattice enthalpies directly by experiment, we use an indirect method where we construct an enthalpy diagram called a Born-Haber cycle, Fig 6.9. Let us now calculate the lattice enthalpy of Na plus Cl, S, by following steps given below. 1 Na, S, Na, G, sublimation of sodium metal, sub H is equal to 108.4 kJ/mol1. 2 Na G Eg, plus 1, the ionization of sodium atoms, ionization enthalpy IH is equal to 496 kJ/mol1. 3 1 2 2 close, G, Cl, G, the dissociation of chlorine, the reaction enthalpy is half the bond dissociation enthalpy. 1 2 bond H is equal to 121 kJ/mol1. 4 Clg Eg Clg, plus 1 electron gained by chlorine atoms. The electron gain enthalpy, H is equal to 348.6 kJ/mol1. You have learned about ionization enthalpy and electron gain enthalpy in Unit 3. In fact, these terms have been taken from thermodynamics. Earlier terms, ionization energy and electron affinity were in practice in place of the above terms. See the box for justification. Fig. 6.9 Enthalpy diagram for lattice enthalpy of NaCl5. NaGClG NaClS+++. The sequence of steps is shown in Fig. 6.9 and is known as a Born-Haber cycle. The ionization energy and electron affinity. Ionization energy and electron affinity are defined at absolute zero. At any other temperature, heat capacities for the reactants and the products have to be taken into account. Enthalpies of reactions for M, G, M plus, G, plus E, for ionization, M, G, plus EM, G, for electron gain, at temperature, T is RH, T, is equal to RH, 0, plus 0 T RCP dt. The value of Cp for each species in the above reaction is 5 to R, Cv is equal to 3 to R, so, RCP is equal to plus 5 to R. For ionization, RCP is equal to 5 to R. For electron gain, therefore, RH, ionization enthalpy, is equal to E0, ionization energy, plus 5 to RT/RH, electron gain enthalpy, is equal to A, electron affinity, 5 to RT. 2019-20. Chemistry 180. The enthalpy of solution of AB, S, Sol H, in water is, therefore, determined by the selective values of the lattice enthalpy lattice H and enthalpy of hydration of ions, HYDH, as Sol H is equal to lattice H plus HYDH. For most of the ionic compounds, Sol H is positive and the dissociation process is endothermic. Therefore, the solubility of most salts in water increases with rise of temperature. If the lattice enthalpy is very high, the dissolution of the compound may not take place at all. Why do many fluorides tend to be less soluble than the corresponding chlorides? Estimates of the magnitudes of enthalpy changes may be made by using tables of bond energies, enthalpies, and lattice energies, enthalpies. F, Enthalpy of dilution. It is known that enthalpy of solution is the enthalpy change associated with the addition of a specified amount of solute to the specified amount of solvent at a constant temperature and pressure. This argument can be applied to any solvent with slight modification. Enthalpy change for dissolving 1 mole of gaseous hydrogen chloride in 10 mol of water can be represented by the following equation. For convenience we will use the symbol AC. For water HCl, G, plus 10 AC. HCl.10 AC. H is equal to 69.01 kJ/mol. Let us consider the following set of enthalpy changes. S-1, HCl, G, plus 25 AC. HCl.25 AC. H is equal to 72.03 kJ/mol. S-2, HCl, G, plus 40 AC. HCl.40 AC. H is equal to 72.79 kJ/mol. S-3, HCl, G, plus AC. HCl AC. H is equal to 74.85 kJ/mol. The values of H show general dependence of the enthalpy of solution on amount of solvent. As more and more solvent is used, the enthalpy of solution approaches a limiting value, I.E, the value in infinitely dilute solution. For hydrochloric acid this value of H is given above in equation S-3. Importance of the cycle is that the sum of the enthalpy changes round a cycle is 0. Applying Hess's law, we get lattice H is equal to 411.2 plus 108.4 plus 121 plus 496 348.6. Lattice H is equal to plus 788 kJ for NaCl, S, Na plus, G, plus Cl, G. Internal energy is smaller by 2 RT, because Ng is equal to 2, and is equal to plus 783 kJ/mol 1. Now we use the value of lattice enthalpy to calculate enthalpy of solution from the expression, Sol H is equal to lattice H plus HYDH for 1 mole of NaCl, S. Lattice enthalpy is equal to plus 788 kJ/mol 1 and HYDH is equal to 784 kJ/mol 1. From the literature, Sol H is equal to plus 788 kJ/mol 1. 784 kJ/mol 1 is equal to plus 4 kJ/mol 1. The dissolution of NaCl, S, is accompanied by very little heat change. E. Enthalpy of solution, symbol, Sol H. Enthalpy of solution of a substance is the enthalpy change when 1 mole of it dissolves in a specified amount of solvent. The enthalpy of solution at infinite dilution is the enthalpy change observed on dissolving the substance in an infinite amount of solvent when the interactions between the ions, or solute molecules, are negligible. When an ionic compound dissolves in a solvent, the ions leave their ordered positions on the crystal lattice. These are now more free in solution. But solvation of these ions, hydration in case solvent is water, also occurs at the same time. This is shown diagrammatically, for an ionic compound, AB, S, 2019-20. Thermodynamics 181. If we subtract the first equation, equation S-1, from the second equation, equation S-2, in the above set of equations, we obtain HCl.25 AC, plus 15 AC, HCl.40 AC. H is equal to 72.79, 72.03. kJ/mol is equal to 0.76 kJ/mol. This value, 0.76 kJ/mol, of H is enthalpy of dilution. It is the heat withdrawn from the surroundings when additional solvent is added to the solution. The enthalpy of dilution of a solution is dependent on the original concentration of the solution and the amount of solvent added. 6.6 Spontaneity. The first law of thermodynamics tells us about the relationship between the heat absorbed and the work performed on or by a system. It puts no restrictions on the direction of heat flow. However, the flow of heat is unidirectional from higher temperature to lower temperature. In fact, all naturally occurring processes, whether chemical or physical, will tend to proceed spontaneously in one direction only. For example, a gas expanding to fill the available volume, burning carbon in dioxygen giving carbon dioxide. But heat will not flow from colder body to warmer body on its own. The gas in a container will not spontaneously contract into one corner, or carbon dioxide will not form carbon and dioxygen spontaneously. These and many other spontaneously occurring changes show unidirectional change. We may ask, what is the driving force of spontaneously occurring changes? What determines the direction of a spontaneous change? In this section, we shall establish some criterion for these processes, whether these will take place or not. Let us first understand what do we mean by spontaneous reaction or change. You may think by your common observation that spontaneous reaction is one which occurs immediately when contact is made between the reactants. Take the case of combination of hydrogen and oxygen. These gases may be mixed at room temperature and left for many years without observing any perceptible change. Although the reaction is taking place between them, it is at an extremely slow rate. It is still called spontaneous reaction. So spontaneity means having the potential to proceed without the assistance of external agency. However, it does not tell about the rate of the reaction or process. Another aspect of spontaneous reaction or process, as we see, is that these cannot reverse their direction on their own. We may summarize it as follows: a spontaneous process is an irreversible process and may only be reversed by some external agency. Is decrease in enthalpy a criterion for spontaneity? If we examine the phenomenon like flow of water downhill or fall of a stone onto the ground, we find that there is a net decrease in potential energy in the direction of change. By analogy, we may be tempted to state that a chemical reaction is spontaneous in a given direction, because decrease in energy has taken place, as in the case of exothermic reactions. For example, 1,2N2 G plus 3,2H2 G is equal to NH3 G. RH is equal to 46.1 kJ/mol. 112H2 G plus 12Cl2 G is equal to HCl G. RH is equal to 92.32 kJ/mol. 1H2 G plus 12O2 G H2O L. RH is equal to 285.8 kJ/mol. 1. The decrease in enthalpy in passing from reactants to products may be shown for any exothermic reaction on an enthalpy diagram as shown in Fig. 6.10a. Thus, the postulate that driving force for a chemical reaction may be due to decrease in energy sounds reasonable as the basis of evidence so far. Now let us examine the following reactions: 1,2N2 G plus O2 G NO2 G. RH is equal to plus 33.2 kJ/mol. 1C graphite S plus 2S L CS2 L. RH is equal to plus 128.5 kJ/mol. 1 2019-20. Chemistry 182. These reactions, though endothermic, are spontaneous. The increase in enthalpy may be represented on an enthalpy diagram as shown in Fig. 6.10, B. Fig. 6.10 A. Enthalpy diagram for exothermic reactions. Fig. 6.10 B. Enthalpy diagram for endothermic reactions. Fig. 6.11 Diffusion of two gases respectively and separated by a movable partition. Fig. 6.11 A. When the partition is withdrawn. Fig. 6.11 B. The gases begin to diffuse into each other and after a period of time, diffusion will be complete. Let us examine the process. Before partition, if we were to pick up the gas molecules from left container, we would be sure that these will be molecules of gas A, and similarly if we were to pick up the gas molecules from right container, we would be sure that these will be molecules of gas B. But, if we were to pick up molecules from container when partition is removed, we are not sure whether the molecules picked are of gas A or gas B. We say that the system has become less predictable or more chaotic. We may now formulate another postulate. In an isolated system, there is always a tendency for the system's energy to become more disordered or chaotic, and this could be a criterion for spontaneous change. At this point, we introduce another thermodynamic function, entropy denoted as S. The above-mentioned disorder is the manifestation of entropy. To form a mental therefore, it becomes obvious that while decrease in enthalpy may be a contributory factor for spontaneity, but it is not true for all cases. B. Entropy and spontaneity. Then, what drives the spontaneous process in a given direction? Let us examine such a case in which H is equal to 0, i.e., there is no change in enthalpy, but still the process is spontaneous. Let us consider diffusion of two gases into each other in a closed container which is isolated from the surroundings as shown in Fig. 6.11. The two gases, say, gas A and gas B, are represented by black dots and white dots. 2019 to 20. Thermodynamics 183 picture. One can think of entropy as a measure of the degree of randomness or disorder in the system. The greater the disorder in an isolated system, the higher is the entropy. As far as a chemical reaction is concerned, this entropy change can be attributed to rearrangement of atoms or ions from one pattern in the reactants to another, in the products. If the structure of the products is very much disordered than that of the reactants, there will be a resultant increase in entropy. The change in entropy accompanying a chemical reaction may be estimated qualitatively by a consideration of the structures of the species taking part in the reaction. Decrease of regularity in structure would mean increase in entropy. For a given substance, the crystalline solid state is the state of lowest entropy, most ordered. The gaseous state is state of highest entropy. Now let us try to quantify entropy. One way to calculate the degree of disorder or chaotic distribution of energy among molecules would be through statistical method, which is beyond the scope of this treatment. Other way would be to relate this process to the heat involved in a process, which would make entropy a thermodynamic concept. Entropy, like any other thermodynamic property such as internal energy U and enthalpy H, is a state function and S is independent of path. Whenever heat is added to the system, it increases molecular motions, causing increased randomness in the system. Thus heat, Q, has randomizing influence on the system. Can we then equate S with Q? Wait. Experience suggests us that the distribution of heat also depends on the temperature at which heat is added to the system. A system at higher temperature has greater randomness in it than one at lower temperature. Thus, temperature is the measure of average chaotic motion of particles in the system. Heat added to a system at lower temperature causes greater randomness than when the same quantity of heat is added to it at higher temperature. This suggests that the entropy change is inversely proportional to the temperature. S is related with Q and T for a reversible reaction as S is equal to Qt Rev. 6.18. The total entropy change, total, for the system and surroundings of a spontaneous process is given by S total system SIR is equal to plus 0, 6.19. When a system is in equilibrium, the entropy is maximum, and the change in entropy, S is equal to 0. We can say that entropy for a spontaneous process increases till it reaches maximum, and at equilibrium the change in entropy is 0. Since entropy is a state property, we can calculate the change in entropy of a reversible process by SSYS is equal to QSYS Rev. T. We find that both for reversible and irreversible expansion for an ideal gas, under isothermal conditions, U is equal to 0, but total I, SS cis SIR plus is not 0 for irreversible process. Thus, U does not discriminate between reversible and irreversible process, whereas S does. Problem 6.10 predict in which of the following entropy increases decreases. I. A liquid crystallizes into a solid. 2. Temperature of a crystalline solid is raised from 0 K to 115 K. 3 Night COS NACO SCO GHOG plus 2-3 2nd March 1922. 4. HGHG22 Solution. I. After freezing, the molecules attain an ordered state and therefore, entropy decreases. 2. At 0 K, the constituent particles are static and entropy is minimum. If temperature is raised to 115 K, these 2019 to 20. Chemistry 184 begin to move and oscillate about their equilibrium positions in the lattice and system becomes more disordered, therefore entropy increases. 3. Reactant. Night CO3 is a solid and it has low entropy. Among products there are 1 solid and 2 gases. Therefore, the products represent a condition of higher entropy. 4. Here one molecule gives 2 atoms, i.e., number of particles increases leading to more disordered state. 2 moles of H atoms have higher entropy than 1 mole of the hydrogen molecule. Problem 6.11 for oxidation of iron. 4-3 February 1923 FeSOG FeOS plus entropy change is 549.4 Jk 1 mol 1 at 298 K. In spite of negative entropy change of this reaction, why is the reaction spontaneous? RH for this reaction is 1648 times 103 J mol 1. Solution 1 decides the spontaneity of a reaction by considering SSS total cis SIR plus. For calculating SOR, we have to consider the heat absorbed by the surroundings which is equal to RH. At temperature T, entropy change of the surroundings is equal to times 1648 10 298 31 mol K is equal to 5530 Jk 1 mol 1. Thus, total entropy change for this reaction R total S is equal to plus 5530 549 4th. Now let us consider how G is related to reaction spontaneity. 2019-20. Thermodynamics 185. We know S total is equal to SSYS plus SO. If the system is in thermal equilibrium with the surrounding, then the temperature of the surrounding is same as that of the system. Also, increase in enthalpy of the surrounding is equal to decrease in the enthalpy of the system. Therefore, entropy change of surroundings, SO is equal to HT cis is equal to SS total cis is equal to plus HT cis. Rearranging the above equation, T total is equal to TSSYS HSYS for spontaneous process, S total, 0, so TSSYS HSYS, Omicron, HTS cis 0. Using equation 6.21, the above equation can be written as G or GHTS is equal to 0, 6.22, HSYS is the enthalpy change of a reaction, TSSYS is the energy which is not available to do useful work. So G is the net energy available to do useful work and is thus a measure of the free energy. For this reason, it is also known as the free energy of the reaction. G gives a criteria for spontaneity at constant pressure and temperature. I, if G is negative, 0, the process is spontaneous. 2, if G is positive, 0, the process is non-spontaneous. Note, if a reaction has a positive enthalpy change and positive entropy change, it can be spontaneous when Ts is large enough to outweigh H. This can happen in two ways. A. The positive entropy change of the system can be small, in which case T must be large. B. The positive entropy change of the system can be large, in which case T may be small. The former is one of the reasons why reactions are often carried out at high temperature. Table 6.4 summarizes the effect of temperature on spontaneity of reactions. D. Entropy and second law of thermodynamics. We know that for an isolated system the change in energy remains constant. Therefore, increase in entropy in such systems is the natural direction of a spontaneous change. This, in fact, is the second law of thermodynamics. Like first law of thermodynamics, second law can also be stated in several ways. The second law of thermodynamics explains why spontaneous exothermic reactions are so common. In exothermic reactions, heat released by the reaction increases the disorder of the surroundings and overall entropy change is positive, which makes the reaction spontaneous. Absolute entropy and third law of thermodynamics. Molecules of a substance may move in a straight line in any direction, they may spin like a top, and the bonds in the molecules may stretch and compress. These motions of the molecule are called translational, rotational and vibrational motion respectively. When temperature of the system rises, these motions become more vigorous and entropy increases. On the other hand, when temperature is lowered, the entropy decreases. The entropy of any pure crystalline substance approaches zero as the temperature approaches absolute zero. This is called third law of thermodynamics. This is so because there is perfect order in a crystal at absolute zero. The statement is confined to pure crystalline solids because theoretical arguments and practical evidences have shown that entropy of solutions and supercooled liquids is not zero at 0 K. The importance of the third law lies in the fact that 2019-20 Chemistry 186 Table 6.4 Effect of temperature on spontaneity of reactions. RHRSRG description * plus reaction spontaneous at all temperatures. At low T, reaction spontaneous at low temperature plus, at high T, reaction non-spontaneous at high temperature plus, at low T, reaction non-spontaneous at low temperature plus, at high T, reaction spontaneous at high temperature plus, at all T, reaction non-spontaneous at all temperatures. The term low temperature and high temperature are relative. For a particular reaction, high temperature could even mean room temperature. It permits the calculation of absolute values of entropy of pure substance from thermal data alone. For a pure substance, this can be done by summing Qt rev increments from 0K to 298K. Standard entropies can be used to calculate standard entropy changes by a Hess's law type of calculation. 6.7 Gibbs energy change and equilibrium. We have seen how a knowledge of the sign and magnitude of the free energy change of a chemical reaction allows I. Prediction of the spontaneity of the chemical reaction. 2. Prediction of the useful work that could be extracted from it. So far we have considered free energy changes in irreversible reactions. Let us now examine the free energy changes in reversible reactions. Reversible, under strict thermodynamic sense, is a special way of carrying out a process such that system is at all times in perfect equilibrium with its surroundings. When applied to a chemical reaction, the term reversible indicates that a given reaction can proceed in either direction simultaneously, so that a dynamic equilibrium is set up. This means that the reactions in both the directions should proceed with a decrease in free energy, which seems impossible. It is possible only if at equilibrium the free energy of the system is minimum. If it is not, the system would spontaneously change to configuration of lower free energy. So, the criterion for equilibrium A plus B C plus D is Rg is equal to 0 Gibbs energy for a reaction in which all reactants and products are in standard state. Rg is related to the equilibrium constant of the reaction as follows: 0 is equal to Rg plus RT ln K, or Rg is equal to RT ln K, or Rg is equal to 2.303 RT log K. 6.23. We also know that 6.24, for strongly endothermic reactions, the value of RH may be large and positive. In such a case, value of K will be much smaller than 1 and the reaction is unlikely to form much product. In case of exothermic reactions, RH is large and negative, and Rg is likely to be large and negative too. In such cases, K will be much larger than 1. We may expect strongly exothermic reactions to have a large K, and hence can go to near completion. Rg also depends upon Rs. If the changes in the entropy of reaction is also taken into account, the value of K or extent of chemical reaction will also be affected. 2019-20. Thermodynamics 187. Depending upon whether Rs is positive or negative. Using equation 6.24 I, it is possible to obtain an estimate of G from the measurement of H and S, and then calculate K at any temperature for economic yields of the products. 2. If K is measured directly in the laboratory, value of G at any other temperature can be calculated. Using equation 6.24 is equal to 13th June 2010 to 303 314 298 3 times J mol J K mol K 111 is equal to 2.38, hence K is equal to antilog 2.38 is equal to 2.4 times 102. Problem 6.14. At 60 degrees Celsius, dinitrogen tetroxide is 50% dissociated. Calculate the standard free energy change at this temperature and at 1 atmosphere. Solution N2O4, G. To know 2, G. If N2O4 is 50% dissociated, the mole fraction of Find out the value of equilibrium constant for the following reaction at 298 K standard Gibbs energy change. Rg at the given temperature is 13.6 kJ mol 1. Solution we know, log K is equal to 2019 to 20. Chemistry 188 Summary Thermodynamics deals with energy changes in chemical or physical processes and enables us to study these changes quantitatively and to make useful predictions. For these purposes, we divide the universe into the system and the surroundings. Chemical or physical processes lead to evolution or absorption of heat, Q, part of which may be converted into work, W. These quantities are related through the first law of thermodynamics via U is equal to Q plus WU. Change in internal energy depends on initial and final states only and is a state function, whereas Q and W depend on the path and are not the state functions. We follow sign conventions of Q and W by giving the positive sign to these quantities when these are added to the system. We can measure the transfer of heat from one system to another which causes the change in temperature. The magnitude of rise in temperature depends on the heat capacity, C, of a substance. Therefore, heat absorbed or evolved is Q is equal to CT. Work can be measured by W is equal to pxV, in case of expansion of gases. Under reversible process, we can put px is equal to P for infinitesimal changes in the volume, making Rev is equal to P dV. In this condition, we can use gas equation, PV is equal to nRT. At constant volume, W is equal to 0, then U is equal to QV, heat transfer at constant volume. But in study of chemical reactions, we usually have constant pressure. We define another state function enthalpy. Enthalpy change, H is equal to U plus nGRT, can be found directly from the heat changes at constant pressure, H is equal to QP. There are varieties of enthalpy changes. Changes of phase such as melting, vaporization and sublimation usually occur at constant temperature and can be characterized by enthalpy changes which are always positive. Enthalpy of formation, combustion and other enthalpy changes can be calculated using Hess's law. Enthalpy change for chemical reactions can be determined by R if HAHBH is equal to products reactions and in gaseous state by RH is equal to sigma bond enthalpies of the reactants sigma bond enthalpies of the products. First law of thermodynamics does not guide us about the direction of chemical reactions, i.e., what is the driving force of a chemical reaction. For isolated systems, U is equal to 0. We define another state function, S, entropy for this purpose. Entropy is a measure of disorder or randomness. For a spontaneous change, total entropy change is positive. Therefore, for an isolated system, U is equal to 0, S, 0, so entropy change distinguishes a spontaneous change, while energy change does not. Entropy changes can be measured by the equation S is equal to CrevT for a reversible process. CrevT is independent of path. Chemical reactions are generally carried at constant pressure, so we define another state function Gibbs energy, G, which is related to entropy and enthalpy changes of the system by the equation Rg is equal to RHT/Rs for a spontaneous change, Gsys 0, and at equilibrium, Gsys is equal to 0. Standard Gibbs energy change is related to equilibrium constant by Rg is equal to RT ln K. K can be calculated from this equation, if we know Rg, which can be found from temperature is an important factor in the equation. Many reactions which are non-spontaneous at low temperature are made spontaneous at high temperature for systems having positive entropy of reaction. 2019-20. Thermodynamics 189 Exercises 6.1 Choose the correct answer. A thermodynamic state function is a quantity, I, used to determine heat changes, 2, whose value is independent of path, 3, used to determine pressure volume work, 4, whose value depends on temperature only. 6.2 For the process to occur under adiabatic conditions, the correct condition is I, T is equal to 0, 2, P is equal to 0, 3, Q is equal to 0, 4, W is equal to 0. 6.3 The enthalpies of all elements in their standard states are I, unity, 2, 0, 3, 0, 4, different for each element. 6.4 U of combustion of methane is x kg mol 1. The value of H is I is equal to U, 2, U, 3, U, 4, is equal to 0. 6.5 The enthalpy of combustion of methane, graphite and dihydrogen at 298 K are 890.3 kg mol 1, 393.5 kg mol 1, and 285.8 kg mol 1 respectively. Enthalpy of formation of CH4, G, will be I, 74.8 kg mol 1, 2, 52.27 kg mol 1, 3, plus 74.8 kg mol 1, 4, plus 52.26 kg mol 1. 6.6 A reaction, A plus B C plus D plus Q is found to have a positive entropy change. The reaction will be I, possible at high temperature, 2, possible only at low temperature, 3, not possible at any temperature, V, possible at any temperature. 6.7 In a process, 701 J of heat is absorbed by a system and 394 J of work is done by the system. What is the change in internal energy for the process? 6.8 The reaction of cyanamide, NH2CN, S, with dioxygen was carried out in a bomb calorimeter, and U was found to be 742.7 kg mol 1 at 298 K. Calculate enthalpy change for the reaction at 298 K. NH2CN, G, plus 32O2, G, N2, G, plus CO2, G, plus H2O, L, 2019-20. Chemistry 196.9 Calculate the number of kJ of heat necessary to raise the temperature of 60.0 G of aluminium from 35 degrees Celsius to 55 degrees Celsius. Molar heat capacity of L is 24 J mol 1 K1. 6.10 Calculate the enthalpy change on freezing of 1.0 mol of water at 10.0 degrees C to ice at 10.0 degrees C. Fusage is equal to 6.03 kJ mol 1 at 0 degrees C. Cp, H2O, L, is equal to 75.3 J mol 1 K1 Cp, H2O, S, is equal to 36.8 J mol 1 K 16.11. Enthalpy of combustion of carbon to CO2 is 393.5 kJ mol 1. Calculate the heat released upon formation of 35.2 G of CO2 from carbon and dioxygen gas. 6.12 Enthalpies of formation of CO, G, CO2, G, N2O, G, and N2O4, G, are 110, 393, 81 and 9.7 kJ mol 1 respectively. Find the value of RH for the reaction, N2O4, G, plus 3 CO, G, N2O, G, plus 3 CO2, G, 6.13 given N2, G, plus 3H2, G, 2NH3, G, RH is equal to 92.4 kJ mol 1. What is the standard enthalpy of formation of NH3 gas? 6.14 Calculate the standard enthalpy of formation of CH3O, L, from the following data, CH3O, L, plus 32O2, G, CO2, G, plus 2H2O, L, RH is equal to 726 kJ mol 1 C, graphite, plus O2, G, CO2, G, CH is equal to 393 kJ mol 1 H2, G, plus 12O2, G, H2O, L, FH is equal to 286 kJ mol 1. 6.15 Calculate the enthalpy change for the process CCl4, G, C, G, plus 4Cl, G, and calculate bond enthalpy of CCl in CCl4, G. Wappage, CCl4, is equal to 30.5 kJ mol 1. FH, CCl4, is equal to 135.5 kJ mol 1. AH, C, is equal to 715.0 kJ mol 1, where AH is enthalpy of atomization. AH, Cl2, is equal to 242 kJ mol 1. 6.16 For an isolated system, U is equal to 0, what will be S? 6.17 For the reaction at 298 K, 2A plus BCH is equal to 400 kJ mol 1 and S is equal to 0.2 kJ K1 mol 1. At what temperature will the reaction become spontaneous considering H and S to be constant over the temperature range? 6.18 For the reaction, 2Cl, G, Cl2, G, what are the signs of H and S? 6.19 For the reaction 2A, G, plus B, G, 2D, G, U is equal to 10.5 kJ and S is equal to 44.1 JK1. Calculate G for the reaction, and predict whether the reaction may occur spontaneously. 2019-20. Thermodynamics 191. 6.20 The equilibrium constant for a reaction is 10. What will be the value of G? R is equal to 8.314 JK1 mol 1, T is equal to 300 K. 6.21 Comment on the thermodynamic stability of NO, G, given 12N2, G, plus 12O2, G, NO, G, RH is equal to 90 kJ mol 1 NO, G, plus 12O2, G, NO 2, G, RH is equal to 74 kJ mol 1. 6.22 Calculate the entropy